Welcome to the ma135, ma160 calculus. My name is Götz Pfeiffer, and this video is going to be some sort of an overview. I'm going to talk about the integral calculus that we're going to develop during this semester, and relate it a bit to the differential calculus that we've done in semester 1, and give a bit of an outlook of what it can be used for in the context of real-world applications. So let's start with looking back at the general question, what is calculus? Well, in general terms, calculus is the mathematical study of continuous change, and it has two major branches: the differential calculus, which is concerned with rates of change and in particular the slopes of curves. That's what we looked at in semester 1. The integral calculus, which is the topic of this semester, is concerned with the accumulation of quantities and things like areas under or between curves and lots of related things. These two seemingly unrelated problems, slopes of curves and areas between curves, are in fact related to each other by the so-called fundamental theorem of calculus. That's something we're going to see in week 3. A fundamental notion that occurs in both branches, that is common to the differential and the integral calculus, is that of a limit, or more precisely the convergence of a certain infinite sequence or series of values to a well-defined limit. That's the technique we're going to look at in week 2. Calculus has widespread applications in science, engineering, economics, social sciences even, and can solve many problems that the simple algebraic manipulation of formulas cannot solve. Therefore, calculus is an important part of the modern mathematics education. That's the reason we're here. Now, looking back at the differential calculus, the central definition there was the definition of a derivative. That's the derivative of a function f, which assigns to a given real number a new real number, and at the point a, this derivative is denoted by f prime of a, and it's defined as the limit of a quotient, the limit as h goes to 0, of the quotient of f of a plus h minus f of a divided by h. Or in a similar but equivalent formulation, using 2 points a and b on the real number line, it's the limit as b approaches a of the quotient of the difference of the function values f of b and f of a by the difference of the x values b minus a. We've seen there that the derivative can be interpreted in many useful ways. For example, f prime of a can be seen as the slope of the tangent at the curve y equals f of a at the point a f of a in the xy plane. That's the slope of the tangent to the graph of the function, and using the point slope formula of a straight line, the equation of that straight line, which is the tangent, can be written down using the derivative as y equals f prime of a times x minus a plus f of a. And that's how the derivative is a precise description of the notion of the tangent of a curve. More towards real-world applications, f prime of a can be seen as the instantaneous rate of change of f of x at x equal to a. As such, one can assign to each point x a derivative, and then the derivative f prime of x becomes a function in its own right. And we've seen ways of finding the function which is the derivative from the given function f. The prime example here is an object moving along a straight line, where if you use a function f of t, a function of time, to measure the distance traveled by this object at time t, then the derivative f prime of t, the instantaneous rate of change in the distance traveled, of course, is the object's current velocity at point t in time. And we'll come back to this example in the context of the integral calculus later. And there we've listed some differentiation rules that allow us to compute quickly, to write down quickly the derivative of a given function without going through first principles, without an actual limit calculation. And we have the power rule, which describes the derivative of a power function x to the a as a times x to the a minus 1 for any exponent a, any real exponent a. And then we have a collection of rules that describe how to compute the derivative of a function that somehow relates to other functions as a multiple or a sum, and the c multiple of a function. The derivative of c times f is c times the derivative of f. The derivative of a sum is the sum of the derivatives. The derivative of a difference is the difference of the derivatives. Then we've seen that the exponential function is its own derivative, which is some remarkable result in its own right. The product rule describes the derivative of a product of f and g, not as the product of the derivatives, but as some sum of mixed terms here, f times g prime plus g times f prime. Similarly, the quotient rule describes the derivative of a quotient. Then there are derivatives of trigonometric functions, which often are trigonometric functions themselves, like the derivative of the sine function is the cosine. The derivative of the cosine in turn is minus the sine function, and so on. And the last but not least on this list, my favorite, the chain rule, describes the derivative of the composite of two functions, f composed with g, as the product of the derivative of f with the derivative of g. We're going to have opportunities to look back at these rules from the point of view of integral calculus and how they can help us there as we go along. For now, I'd like to look at one aspect of differentiation that leads to one of the topics we'll cover in the integral calculus that's concerned with differential equations. Now, just as a brief introduction, we'll look at this in more detail and with more time later on. The message here is that the calculus, the language of calculus, enables us to express simple observations about real-world phenomena, about rates of change in real-world contexts in terms of functions and their derivatives. One example, again, we'll have time to go back to this in more detail later. One typical example of this is population growth, where one might find that a certain population, denoted by p, grows over time at a rate that is proportional to its current size. Now that's a description in word which makes perfect sense. Populations grow, and the rate at which a population grows it makes sense to describe it as being proportional to its current size. In the context of calculus, this can be described as a function. Now we can describe population p as a function p of t of time t, and then its rate of change is its derivative, denoted by p prime of t, the derivative of p with respect to t. And to say that p prime is proportional to p means that at each point in time p prime is a constant multiple of p. Say it's the k multiple for some real number k. And we can express this as an equation, p primes equals kp. More precisely, we can translate this statement in words into a so-called differential equation, which is an equation between functions and their derivatives, as follows: p prime of t equals k times p of t. And as equations do, this equation has a solution. This equation has solutions p of t of the form a times e to the power kt for any positive a. And that's something you can verify with what you learned in the differential calculus by calculating the derivative of a function that is defined by such a formula, and then verifying that this derivative is indeed k times the formula that defines the original function. We will see later that the functions of this form are indeed the only solutions of this differential equation, and for this we'll develop first the integral calculus. Differential equations will be covered in the later section of the course. But just to emphasize this point a bit more, how differential equations can be used to model real-world phenomena, let's look at the problem of modeling a pandemic. A simple and rather popular model for modeling a pandemic is the so-called SIR model, where a population of capital N people is subdivided into three groups called S, I, and R, where S is the group of susceptible people, I is the group of infected people, and R is the group of recovered people. So we have S people, which are susceptible, I people infected, and R people recovered. And then there are certain possible transitions from one group into another, described by a parameter b, a contact rate b, which describes the likelihood of susceptible people becoming infected, and another transition from the I group into the R group, described by a parameter a, describing the likelihood of infected people to recover. So here in this model, the sum of these three numbers, S, I, and R, is always n, the total size of the population. The sum is constant. The contact rate describes the transition from susceptible into the infected group, and the cure rate A describes the transition from the infected group into the recovered group, and it's somehow inversely proportional to the length of the infection, to the infectious period. Similar to the population growth in the previous example, the relationships between these three groups of people can be described in terms of differential equations relating rates of change to the functions themselves. For example, if we start at the end here, the rate of change in the group of the recovered people, the rate at which the number of recovered people increases, can be described as being proportional to the current number of infected people. If A is the cure rate, the rate at which infected people recover, then it makes sense to say that the rate at which R increases is A times the current size of I. It's similar to the population growth formula we've seen before, just that now it involves two functions, R and I, and what it states is a relationship between the derivative of R and I, and the I function. Now, similarly, the derivative of S, the rate of change in the group of susceptible people, the rate at which the number of susceptible people decreases can be described as being proportional to, now here it's the product of S and I. Now the size of I, the number of infected people times the number of susceptible people. It's the product of these two quantities which describes the total total possible contacts between infected and susceptible people. And if they get infected at a rate B, then it makes sense to describe the rate of change in S as minus B over N times the product S times I. Now here things are normalized in such a way that one divides by N the total number, the total population. And then, since the sum of all these three numbers is always the same, is always constant, the rate of change in the I group has to make up for the rates of change at the ends in S and R. So it's the negative of the sums of these two rates of changes. And that's a simple model using the language of differential equations. And then one can use this model to ask and answer simple questions, like, for example, when is the number of infected people going down? Now, from the differential calculus, we know that a function is decreasing if and only if its derivative is negative, strictly less than 0. The model here involves a formula for the derivative of the I function. It's b over n times s minus I minus a times I. To have this negative, we can reformulate this inequality and get b over a must be less than n over s. This b over a, by the way, is often called the R0 of this model, which has been mentioned a couple of times recently. So in order to get the number of infected people decrease, this inequality needs to be satisfied. And so the inequality immediately suggests 3 ways of trying and to decrease the I number. Namely, in order to get this, to satisfy this inequality, one can try to get the b parameter down, or one could try to get the a parameter up. If we make a bigger, the inequality becomes more likely to be satisfied. Or one could try and decrease the s number. In practical terms, this means that the contact rate should be decreased. That's and in terms of that's your social distancing and to reduce your contacts. Or one could try and increase the A parameter. That is increasing the cure rate. For this, some cure would have to be invented. Or, third possibility, one could try and decrease the number of susceptible people, for example, through vaccinations. That's 3 measures being suggested from this simple model. For more detail, one can use this model as a simulation and then find and maybe set up a graph of how these numbers S, I, and R evolve over time. So this here is for a particular choice of the A and B parameter, a 300-day period. Now we're starting with almost no infections at all. The numbers go up and then slowly go down towards 0 again, with the number of susceptible people going down all the way and stabilizing at some point here. And on the other hand, the number of recovered people going up and stabilizing somewhere here. We look in more detail at the subtle features of this model at a later stage. For now, that's it. And next, we're going to look at area problems.